Me dice, ¿quieres volver a cargar el sitio web? Evitar que la página cree cuadros adicionales. Me sale ese mensaje ahora, ¿no? A ver. ¿Tendría que ingresar nuevamente a la reunión?
No, porque usted ya está en la reunión y nosotros podemos ver su presentación.
El problema es que no tengo la presentación a la vista.
Debe estar minimizada.
Sí, puede estar abajo.
¿Abajo?
Sí, así a veces se minimiza, entonces hay que...
A ver, ¿dónde está? Cancelar, dice.
No.
Next is verify. It's just verify it's you. Okay, enter password. It's a problem of Google. Okay, protect your account, confirm. Okay.
Pero la puede ver en el YouTube, entonces va viendo la lámina que va saliendo.
A ver, loading email, okay, that's it. Okay, ahora, let's go to Jessica Noemi Flyer. Está viendo mi campaña, ¿no? A ver, ahora voy a dejar de compartir y voy a entrar de nuevo, no sé qué puedo hacer, no veo mi pantalla.
Dejar de compartir y volver a compartir.
Y vuelve, sí.
Ya, entonces dejo de compartir, ahora sí, comparto la pantalla otra vez, aquí, ok. Ahora sí.
Buenos días a todos, Marta. ¿Qué tal?
Oh, hola Marta, buen día.
Buenos días. Ahora sí, está bien, Ramiro, sí.
Excelente, gracias.
Buenos días.
Buenos días.
¿Qué tal, Ramiro? Soy Jesús.
¿Cómo está Jesús? ¿Qué dice? Un gusto.
Pues por aquí a ver qué nos cuentas.
No, bueno, ya sabes de lo que se trata.
Muy bien. Tendré apagado el micro.
Ok.
Saludos para todos.
Gracias. Lo haré presente.
Saludos, Jesús.
So I think we are ready to start.
Yes.
Okay.
Yes.
Okay, so you start, Noemi.
Okay.
Perfect.
Good morning. We're going to start with the last webinar we have for this time. And now we have a presentation by Dr. Ramiro Escalera. I will present him. He's a full professor, director of the Center of Research in Industrial Processes at Universidad Privada Boliviana. About his academic training, Dr. Escalera is postdoctorate research associate in Chemical Engineering Department of Shizuoka University, Japan. His doctor in engineering mentioned in chemical engineering at the same university, Shizuoka, Japan. Master of Engineering mentioned in Sanitary Engineering, Shizuoka University, Japan. And his Chemical Engineering from the Universidad Mayor Real y Pontificia San Francisco Javier de Chuquisaca, especially in biological treatment of municipal and industrial waters, development of advanced photo-oxidation processes for water purification and removal of pollutants in industrial wastewater. Academic and professional activities at the Universidad Privada Boliviana. He's full professor since 2017 and titular professor at the same time in careers of production engineering and petroleum engineering of the Faculty of Engineering and architecture, consultant of 3 national commission of management of the Pilcomayo River Basin, executive director of the Institute of Food Technology, head of Processes Laboratory, Institute of Food Technology, visiting professor at the Faculty of Technology, Universidad Mayor Real y Pontificia de San Francisco Javier de Chuquisaca, research associate at Chemical Engineering Department, Shizuoka University, Japan, in 1991. He has more than 40 publications in Bolivian and international journals and has participated in international conferences on chemical engineering as lecturer, and his research has received several awards from the Bolivian Vice Ministry of Science and Technology and the Chamber of Industries of Cochabamba. Thank you, Professor Ramiro Escalera. Please, you can start with your talk.
Thank you very much for the presentation and the opportunity to share this research titled The Arsenic Removal Using Photoreactors in Small Rural Town Located in the Bolivian Altiplano. This investigation was carried out together with Dr. Omar Ormachea, which is director of the Centro de Investigaciones Ópticas y Energías at the Bolivian Privada Boliviana, Universidad Privada Boliviana. Well, we are going to describe as the arsenic occurrence in Cochabamba, which is new for us, and the components of the removal system, and which we will describe the development of the SORAS continuous process that we made, and the iron oxide coated sand utilization of this kind of filters and media. And then we will show the characteristics of the Fresnel type photoreactor, the performance of the system, and the conclusion. Well, our interest in studying the arsenic removal treatment systems occurred when we discovered, together with Mauricio, the arsenic occurrence in Cochabamba at the beginning of this decade. So it was a casualty. We didn't know that the Cochabamba Valley had a naturally arsenic occurrence. So we are showing here the results of the sampling campaign that we made in November 2018, in which we sampled 39 wells, and these wells were 40 to 120 meters deep. The photograph shows the spatial distributions of the wells in the whole valley in Cochabamba. So we found a mean value of 13 ppbs with a maximum value of almost 80. And interestingly, we have this result that 28% of the well presents concentration above the World Health Organization maximum limit value of 10 ppb. In 2019, we made another campaign of sampling in which we sampled 38 wells located as shown in this photograph. And we found almost similar contents of arsenic, and the maximum value was a little bit higher, of 113 ppbs. This well is located at home, in my home, and that's the maximum value. So I have to treat my water. So 30% of the wells presented the concentrations above the WHO maximum limit. Well, this study is going to be completed by Mauricio, who will study the hydrochemistry of this distribution, the arsenic occurrence of in this valley of Cochabamba. Okay, as many of you know, the solar oxidation and removal of arsenic, solar process, was developed by Wegeling in the late 1990s. And here he shows a PET bottle and the solar UV radiation in a water solution, which has naturally a high content of ferrous ion, and an arsenic 3 concentration up to 500 ppb. And they added 4 to 8 drops of lemon juice as a citrate source. So in the process, the UV radiation generates free radicals of high oxidant power, like anion superoxide and hydroxyl, and the hydrogen peroxide, which are strong oxidants. And in this way, the arsenic 3 is oxidized to arsenic 5, and the arsenic 5 is adsorbed in the already formed iron hydroxide surface. In this matter, they co-precipitate sedimentate in the bottle. So by filtering the decanted water, you could achieve a reduction of the arsenic content and the iron content, as shown here. Okay, the UV radiation in Bangladesh, where this experiment was done, the UV radiation intensity varied from 80 plus minus 20 watts per square meter. And they achieved removal efficiencies in the order shown here, obtaining a value of total arsenic less than 50 ppb that at the time satisfied the Bangladesh guidelines limit. Chilean researchers, Cornejo and collaborators, modified this storage process. This time they treated high salinity surface water that did not contain iron ions, but had a very high concentration of arsenic 3 and 5. They used 1 to 2 grams steel shavings, 1 drop of selected lemon juice, exposed to 6 hours of solar UV radiation, and they obtained good removal efficiencies above 99%, and the quality of the treated water had achieved and satisfied the World Health Organization limit value. This photograph corresponds to this research. You have here 10 bottles of 2 liters, and almost the area is about 1 meter. So with this, we have the capacity of a collector of this treatment system. Very simple, but the limitations are obvious here. Small capacities, long times of irradiation that are suitable only for drinking and cooking only. Not too convenient for schools, larger families, sanitary centers, animal water needs, or crop irrigation that in the rural area are needed. So we need a low-cost continuous treatment system of larger capacity. We know that the solar concentrators will multiply several times the incident UVA radiation, and this could accelerate the whole process. So in this time, at the time, we built a low-cost semicircular section solar concentration, very cheap, because we used very cheap materials like PVC split tubes and neon spent tubes, neon light, no, spent tubes, and aluminum foil. So we used the neon tubes because they have a higher transmittance value compared to the PET bottles in the range of the UVA radiation interval of the spectra in nanometers. Okay, this photoreactor built in this way was compared with a PET bottle and a tube, a neon tube alone, under the same conditions of irradiation. And this time we used spiked distilled water with 1,000 ppb of arsenic pentavalent. We used the molar dosage optimized by Lara and collaborators, the proportion of arsenic citrate and ferrous ion, 1:5 to 19 in molar basis. We aerated for several seconds the solutions, and we exposed the system to some time, and we took samples at convenient time intervals. Well, the results in this flow growth kinetics up to a size of 0.45 micrometers, which is the pore size of syringe filters. We observe here that the concentration of arsenic is dramatically reduced, and from 1,000 ppb to a few tenths of ppbs. The photoreactor is a lot faster than the tube alone and the PET bottle. Okay, we again compared this time 4 photoreactors of different size, of concentration capacity varying from 2.8 sons to 70, also to 10 sons approximately. And this time we used, instead of distilled water, we used groundwater spiked with arsenic pentavalent with 1,000 ppbs. We also aerated the solutions, we exposed for several minutes, and we made two kinds of experiments. One without agitation, just taking samples, and the other experiments were followed by controlled agitation. Okay, the results without agitation shows the flow growth kinetics up to a size of 0.45 micrometers. And we observe here that the largest concentrator was able to reduce the arsenic concentration very rapidly compared with the another photoreactors. Okay, when we made the controlled agitation experiments, we observed the formation of flock size up to more than 0.5 millimeters in the system. And we calculated the effective UV radiation intensity in the solution. And there was a linear relation with the flock growth velocity measured as micrometers per minute. One interesting result here is that the largest capacity concentrator only needed 3 minutes of exposition to generate a flock size that is has good setability. And here in the photograph, you have the system and the flock appearance in this vessel that is usually used for a controlled agitation of this magnitude of 33 seconds to the -1 of a velocity gradient. Okay. After that, we constructed the photoreactor prototype of continuous flow. In the figure you show in the tank is this water with the reactants that is aerated at several seconds, minutes, and the water flows by gravity through the photoreactor and is collected in another container here. And we also constructed a pilot prototype. This time we used 4 photoreactors of the largest capacity of concentration capacity of 10 tons. And here we observe that the generated formated floccules sedimentate in this acrylic sedimentator. So in this way, we have the results of the photoreactor prototype, and we show here that in the continuous system, the hydraulic rotation time, excuse me, retention time only needs only is 15 minutes in this photoreactor to achieve a good settable flock size of about 1 millimeter of size. The system has achieved a removal, arsenic removal more than 98% in decanted waters, and they reduced the total arsenic from 1,000 to 16 ppb. Excuse me, please. Estoy en un webinar, por favor. Sí, sí, por favor. Yeah, yeah, please. Yes. Okay, excuse me. Okay, the treatment rate calculated in these conditions was 130 liters per square meter per day when the system was exposed for 5 hours to UVA radiation of 45 to 65 watts per square meter. In the continuous pilot prototype, we also made the experiment for 2 weeks in groundwater at the university here in Universidad Privada Boliviana in the cafeteria. And we obtained the arsenic removal efficiencies over 18, and we achieved concentrations in the treated water that were less than the limit of detection of the apparatus. So this removal is estimated. So the treatment rate here is increased to 160 60 liters per square meter per day, with a range of 3 to 4 hours of exposure, the intensity of 43 watts per square meter. Okay, the another component is the absorption process, which uses the iron oxide coated sand, which is a low-cost media because this is a residual sand that can be obtained from the treatment plants of for iron and manganese filtering systems. We bought this media as shown in the figure, was bought from an industrial installation in Cochabamba. And the price was very low, almost only $3 per 50 kilograms. The absorption capacity reported by another researchers is shown here, up to 0.64 milligrams of arsenic per gram of sand. This media also has a high specific superficial area up to 230 square meters per gram, measured as the BET method. Well, the design parameters for the design of the filters, we have these conditions: the empty bed contact time of 30 minutes and a linear velocity of 5 meters per hour. Well, the absorption process, as described by Petrusevsky, goes like this. The arsenic 3 and arsenic 5 are absorbed over the surface and active sites of the IOCS media, and once they saturate the active surface, regeneration is needed, where a ferrous salt is added to the water, and it forms another layer of this iron over the arsenic layer shown here. And dissolved oxygen present in water will oxidize this layer to form another layer of ferric oxide. And in that surface, again, the arsenic 3 and arsenic 5 will be absorbed again. In this figure, we show the geometry of the Fresnel type photoreactor. We used these materials, aluminum foam and supports, anodized aluminum sheets, which has a reflectance very high of 0.92, and that covered the frames and to reflect the radiation. And as in the collector, in the upper part of the collector, we installed an acrylic tube of high transmittance of 0.91. The PVC tube here is a secondary collector on whose surface also was attached the anodized aluminum sheet. Okay, we have here the photograph of the constructed photoreactor, and the concentration goes this way. The incident UVA radiation is reflected towards the acrylic tube by the position, varying position of these surfaces. In detail, we have this radiation that is reflected in this surface and goes to the acrylic tube. And the radiation that goes through the acrylic tube is also collected in a secondary collector and returns again to the solution. In this way, we multiplied an incident of 60 watts per square meter up to 150 watts per square meter, giving a concentration capacity of 17.5 SANs. Here we have the arsenic removal system scheme. For a Quillacas installation, we have this storage tank and the water is introduced and is aerated by a commercial spray, and the reactants are automatically fed to this current by a peristaltic pump. The water with the reagents is pumped to the photoconcentrator, the reactor, and then is filtered in 2 filters of iron oxide coated sand and sequential way. The treated water is collected in this storage tank, and the water is pumped to the point of use automatically. When you open the valve, the pump functions, but it goes through a microfilter of 5 micrometers of pore size, followed by another microfilter of 1 micrometer of pore size. Okay, in Quillacas, we installed this system. You see the photographs. Here we show the peristaltic pump and the storage first tank. This goes to the 2 filters connected in series, and the treated water is collected in this tank, and after that is pumped to the tap water point of use, but the microfilters are connected here in series. Okay, Quillacas is a small town with a population of about 2,000 inhabitants, located in the southern part of Popo Lake. The treatment capacity was designed for 1,500 liters per day, and we installed the system at an elementary school with 85 students, and the operating strategy was that in cloudy days and nights, as the system is automatic, the filtering is the only process, and we use the photo collectors on sunny days. Okay, here we show the Photoreactor Platform. There are 6 photoreactors connected in series, and they are oriented to the north. Okay, the performance was as follows. The operating conditions for IOCS filters and photoreactor were as recommended by designers. The hydraulic retention time in the photoreactor tubes was about 1.5 to 1.7 minutes, as expected by the capacity of the concentration of solar UVA radiation that we experimented before. The UVA intensity measured in Quillacas varied from 45 to 60 watts per square meter, and the reactants were 5 to 8 milligrams per liter, and a citrate dosage of 7 milligrams per liter. We observed that the water consumption of the population, the students, it was very low. Only 10 to 15% of installed treatment capacity is used. The important thing is the untreated water quality that is measured in this town. The pH and ORP presents a moderate oxidant activity. The water is saline, with high concentrations of sodium chloride. There is no phosphate, which is a competing ion on the active sites of the ferric oxides in the flux and in the sand. And the sulfate is moderate, concentration moderate, and the nitrate the same way. Boron concentration is very high, almost to 3,000 ppb. Under these conditions, we observe here the treatment period beginning from September 2019 up to beginning of February 1920 of this year. And we observe here a good removal efficiency, more than 95%, achieving concentrations up to 5 milligrams per liter, satisfying the Bolivian guideline limit value. Here, in a certain time in the filters, we provided a generation adding a ferrous salt. Okay. Okay. Well, the conclusions are that the system is efficient, achieving overall arsenic removal efficiencies of 95%. The boron seems to not interfere, and the system is suitable for high conductivity, high salinity waters. The system is able to provide safe water to 800 persons at 2 liters person per day. This number represents 30% of the population. And the water, untreated water quality is appropriate for the treatment, and there are reasonable chemicals doses. Okay, we have a lot of work to do. There are sample remaining, sample analysis remaining. We communicate with the operator by WhatsApp, and they are conserving the samples to be transported to Cochabamba for the analysis. We need to characterize the iron oxide coated sand, which is in progress now, with the help of the Spanish researchers who collaborated with us in this project. And we have to determine the operating costs per cubic meter. That depends strongly on the consumption rate of treated wet water. And after that, we will analyze the possibilities of scaling and replicability of the system. We have published this content in indexed journals, presented in international congress, and published also. This work was published at the Universidad Privada Boliviana journal. We want to thank the Universidad Mayor de San Andrés, who collaborated in this research, el Instituto de Geológico y Minero de España, Geólogos del Mundo, la ONG, and this project was financed by the Spanish International Cooperation Agency for Development, AECID. Thank you for your attention.
Marta Litter has questions.
Yes.
Thank you.
Can you hear me?
Yes, a little bit louder.
Okay, okay. Nice to meet you.
Nice to
Dr.
meet you
Escalera.
too, Marta.
Okay. Regarding the SORAS method, we have also worked with it. And my question is not only for you, but also for me. How much arsenic-3 do you have in your waters? To see, let me finish. And if it is necessary to use solar light, if you don't have arsenic-3, and how much iron do you have in your system before and after the treatment, and what was the pH of the system?
Okay. Well, the quality of the water in Quillacas has an arsenic pentavalent more than arsenic-3. Almost 90% of the total arsenic is distributed that way. So the iron concentration goes around 0.3 milligrams per liter.
Excuse me,
not so much.
Can you repeat the concentration of arsenic-3?
Arsenic-3, well, the concentration of arsenic-3 in the distribution, we showed that varies, the total arsenic varies from 40 ppbs up to 80 ppbs in the period of time. Of those concentrations, we measure arsenic-3 in some samples, and we have a 90% of arsenic-5, and the rest is arsenic-3 in this well water. Because the operating activities, operating conditions that the well has, and well, this is a well approximately of 80 meters. It's not so deep, but these are the conditions of the untreated water with respect to arsenic. Respect to ferrous iron, the content is very low. It's almost 0.3 or 0.4 milligrams per liter. Not enough to accomplish the solar UV, the SORAS process. So we need to add ferrous salts in the process.
Yeah, the pH was?
The pH varied from, as shown in the table, okay, above 6, 7 to 7.5.
Okay, this for the SORAS method.
This is for the untreated water treated by the hybrid system. So we combined, as you know, as you saw, the solar collector with the iron oxide coated sand filters. Okay.
Okay. Okay. Thank you very much for your contribution. That was excellent. Thank you.
Thank you very much to you, Marta.
We're going to continue with a question from Juan Pablo Zamora. He's asking, have you considered to adapt and test these modules in other Bolivian regions like Chaco Plain?
We are not in that possibility yet because we don't know the concentrations of arsenic in that region. we have to assess the arsenic occurrence in that region first in order to view the possibility of a replication of this system in small rural towns in that area. Mauricio would explain better than me how is it going, the sampling in Tarija region, to answer the question.
Well, we sampled a few wells there in south of Bolivia, in Tarija, it's near Argentina, but we didn't find arsenic in that wells. But at the same time, it's not much wells. We only have around 12 groundwater wells. So still we need to go there again and collect more samples to be if they contain arsenic. But we know that also if we sample more in the Altiplano region, we probably will find more arsenic than in the valleys. Okay.
We have another question from Caroline Meyer. It's so what was the water quality after treatment? And the other, did you get a lower salinity and less boron? Was there a difference between use of the photoreactor during the day and of the filter system during the night? Those are 3 questions.
Yeah. Okay, the first question, where was the water quality at the end of the treatment? Well, the arsenic, total arsenic was measured. Total means that the particulate arsenic and dissolved arsenic were measured at the analyzer, no? We used hydride regenerations and atomic absorption system method. And we also have to measure the iron content, but we expect the iron content to be lower because we are filtering it with a porous size of a microfilter of 1 micrometer pore size. And in the Solar's process, when you filter the water, the concentrations of iron, dissolved iron, will be less than 1 milligram per liter. Okay, and that is about the purpose and the quality of water at the end of the treatment system. The another question was,
did you get a lower salinity and less boron?
The boron was not removed. We didn't measure this, but we don't expect the reducing the boron. But we have to measure that in order to assess this quality or to assess the performance for boron. Okay.
And the third question, did you get a lower salinity? Was there a difference between use of the photoreactor during the day and of the filter system during the night?
Well, the system operated mostly with filtering only because it is automatic. And the automation accumulates about 1,000 liters in the tank, and as the water consumption is only 100 liters per day, the system works when the volume is consumed automatically. So we have to operate the photoreactor when the water is consumed, the tank is empty, open the photoreactors exposed to the solar light, and treat the system. So we have to assess that. Also, we didn't differentiate so far this contribution of the photoreactor and the filtering system. The removals that you are seeing is mostly achieved by the filtering system.
And we have a last question in the chat of Zoom. Did you study the influence of other ions, namely bicarbonate on arsenic absorption capacity?
Well, the bicarbonate here, we don't have the information here in this this follow up of the treatment system. But the bicarbonate is present in the water. It will neutralize if we add the citrate, the pH will lower a little bit, but the bicarbonate will be a buffer, and the pH will not decrease considerably in the treatment. So what we know is that the bicarbonate is the content of bicarbonate will help to the formation of the ferric hydroxide in the system. That will be the effect of bicarbonate ions in the treatment system as a whole. Okay.
There are no more questions in Zoom.
I have a question for Ramiro. If after the filtering and in the tank where you keep the water without arsenic, if you have noticed the precipitation of salts or other minerals in the tank?
Not actually. So far in my visits, I didn't see the coloring of the tank, which is a sign of that the hydroxide is added, to the surface of the tank. We didn't see that so far. Anyway, the filtering system is going quite well. The velocity of the water flow is very slow. So the retaining capacity of the filters is good. So we have a good quality water in the tank. And after that, we are microfiltering the water. And we changed by the filters once in this period. And we saw a slight accumulation of ferric oxides in the filtering. So the microfilters could be used for longer times and be as good as the beginning.
Ramiro, this water is only used in the school, or there are other families that could also go and take some water for their drinking and cooking, or it's only for the school?
Well, the purpose of the project was to provide safe water to the students, elementary school students. But the consumption was rather low. So we communicated this situation to the rural authorities, the community leaders, and they constructed tap water installation outside the school. So nowadays, because the students are not going to the school, there is an increase of the water consumption to 220 liters per day as a mean, as an average. So the population is consuming our treated water. The students are not attending the school nowadays, and because of the pandemic. So the real consumption is that. Probably they will decide to construct another point of uses that will provide larger water consumption to the population. And as I mentioned, the capacity of the treatment system will provide at the rate of 2 liters per day of consumption for a person, that represents a third of the Quillaca's population of 2,000. So the people is very enthusiastic of using this water for drinking and cooking purposes mainly.
So do you think that maybe this could be like the starting of a kind of distribution, instead of making a filter in each house? It's better to have 2 or 3 of these plant treatment in the basin, and it could be in such a way that the communities can be organized and take that water. Maybe this could be the...
Yeah, it's very possible. The population, the community leaders are asking to expand to the total population more point of uses of the same system, and of course 2 or 3 treatment systems in appropriate places could be installed, and they will provide safe water for drinking and cooking purposes only, not for showering and other needs. But this is the kind of project that the purpose of this project was to provide safe water for drinking and cooking.
Thank you.
I would like to add something about that, Jessica.
Yes.
Quillacas is one of the biggest cities in that area. They have around 3,000 inhabitants there. But in the area, there are at least more than 50 small communities, but they are dispersed and spread in all the area. So this treatment plant was constructed in Quillacas because they have more population there. But what happened in the other communities, small communities, so they cannot, it's not possible for them to put a treatment plant. So they need to use another kind of treatment system for their water. Of course, their water is also contaminated with high arsenic concentration. So we need to maybe to use the SORAS method or some other kind of method. As Quillacas, there are some other big towns like Pampauriagas and Cebarullo. So maybe we can replicate this treatment plant in these bigger cities or towns in the area. But for the small communities, we need to use another treatment, water treatment.
Good.
Mauricio.
Thank you, Mauricio.
Mm-hmm.
Thank you, Ramiro. Thank you very much for your interesting talk.
Okay, thank you, Paul.
It's very nice to see how a direct application in our region. Yes.
I have a couple of questions.
Okay.
Very nice presentation, Ramiro, and very nice system you have set up. One thing I don't quite understand, it's well known that sunlight manages to do iron photoreduction, that is, reduces dissolved iron in the water to the +2 state. And yet you manage to get it so it's oxidizing the iron. I'm wondering if that's because in your process, the iron oxidizes, for some reason it oxidizes faster, maybe because of the pH, than it can reduce by the sunlight.
That is probably so. But in the studies I read, the range of pH is varies from 7 to 8 approximately. And this range of pH is appropriate for the storage process. So the oxidation of iron will proceed. And ORP is also a little bit high. And those conditions of pH and ORP will enhance the appearance of arsenic 5 instead of arsenic 3 by the application or reaction of the free radicals. So I don't expect a reduction of what you meant. I didn't answer quite well, the respect to the ions.
Did you want me to explain that?
Yeah, please.
Yeah, there's several papers in the literature that go back quite a ways, demonstrating that sunlight photo-reduces iron in surface waters. And it happens regardless of pH, regardless of salinity. And it's well documented. So there must be some reaction going on in your system where the oxidation somehow is going on faster than the reduction by sunlight. And it maybe has to do with the availability of oxygen and the something to do with the capacity of the oxygen relative to the amount of water that's flowing through the system somehow. But it's an interesting thing that you've got it to work so well.
Yeah, I think so. We have to monitor the iron concentrations a lot better than we did so far. Thank you for your comment.
Yeah, I have a one or two other quick questions. I'm glad that Maria brought up the question about the bicarbonate absorption, but another ion that you should look at is fluoride, because fluoride is often elevated in waters that are elevated in arsenic. And it may be that with the iron flocculation that you're getting fluoride taken out as well. So it'd be good to monitor that.
Yeah, the content of fluoride in this water of Quillakas is very, very low. So it's not a competing ion. But in other regions of, like in Santa Cruz, Mauricio found a lot higher fluoride concentrations in the zone of the San Pedro, the northern part of Santa Cruz in Bolivia. And they also have had, as you said, a high concentrations of arsenic. So this question or this situation should be researched, should be investigated. What is the what would be the, for example, the use of the IOCS system and the fluoride removal together with the arsenic removal? Should be interesting to research that, I think.
Yeah, yeah. My last question has to do with the, well, it was partly answered earlier about having to clean the system, how often you have to do that. But it doesn't sound too bad. But the other part of that question is you have this arsenic-rich sediment and that needs safe disposal. And have you considered how to deal with that?
Yeah, there are two aspects here, depending on the consumption of the water. So far, we didn't need to backwash the filters so far in Quillacas. That's a good news. And we have another installation here at Cochabamba, at the university, with a higher consumption rate up to 2,000 liters per day, when the capacity installed here is similar to Quillacas of 150 liters per day. We only needed to backwash for 15 minutes the two filters once in a semester, in 6 months. And we also changed the microfilters once in that period. Well, these residues should be, of course, separated. They will be the flux here, they're accumulated, should be hydrated and dried and disposed in a safe site, an isolated site. But the quantity so far in this at this scale is very small. That's one question. The other one is that once the iron oxide coated sand is saturated with arsenic in the long time, we have to replace the media, and the media should be used safely. One of the possibilities is to use this saturated sand as a constructing, as an aggregate for, how do you say, concrete, in order to build some buildings or some, how do you say, aceras, o sea, some pisos, floors, etc., with that concrete. And it should be a good thing to utilize this spent sand as a constructing material. It would be a safe disposal.
Thank you, Ramiro.
Okay, thank you, Kirk.
Okay, thank you everyone for all the interesting questions. And now if you have some minutes, I would like to show you present an acknowledgement to all our attendants. So I'm going to share my screen.
Okay,
I think it will stop automatically.
Okay.
Let's see. Yes.
Okay. Thank you.
I think it did. Okay, so can you see my screen now?
Yes.
Okay. Well, yes, as this year, as we were saying this several times, was very challenging year for everyone, and this webinar gave us the opportunity to still meet somehow and discuss about the arsenic in the environment. And so we want to really thank you thank to all the attendants for participating in our webinars. We did 6 webinars, from 1 monthly from July to December, and we were covering different topics from the origin of geochemistry and geochemistry of arsenic, its effects on human health, the remediation technologies, and we were also showing study cases in the Altiplano Puna region. In total, we had more than 200 participants. Some of them were joining several webinars, and some of them were with us in all of the webinars, and people were attending from more than 14 different countries. Argentina, Bolivia, Brazil, Canada, Chile, France, Mexico, Spain, South Africa, Sweden, Switzerland, Spain, Portugal, Turkey, the United States, and Uruguay. And because of this, the UNESCO put on the official website, they are showing all the webinars, this series of webinars. And so if you want to rewatch, or if you want to share this with your colleagues, you can go to to this website, and you can see and you can find the links for the YouTube videos. You can also join or subscribe to our YouTube channel, which is called IGCP UNESCO 707, and you can find here all the webinars as well. And we also have our social networks, mainly on Facebook and Twitter, and we are starting with Instagram, and so this is going to be the way for us to keep in touch with you for next year. And so, well, finally, we hope to see you soon next year. We hope it's going to be possible to attend meetings soon. But for now, we wish you Merry Christmas, and that have a good starting of 2021. Okay, so that's it. It was very short, but I wanted to really thank all the participants for joining us during these years.
Yeah. Thank you, Jessica.
Okay, well, so we will keep in touch, and thank you very much.
Thank you.
Thank you all, and nice meeting you. Many of you I didn't know, so I've been